Hello. For this video, we will be talking about network models, its formulation, and solution algorithms. Now, before we discuss the different models that we will be eventually learning in this module, let me first define certain concepts and terminologies that we will eventually use all throughout the module. So, so first, let me define what a graph is. A graph consists of a set of nodes and a set of edges connecting the nodes. Nodes are also called vertices or points, and they represent entities, intersections, or transfer points. Edges are called lines, and branches are undirected links between pairs of nodes that represent flow or relationship. Okay, so let me try to give you an idea on what a node looks like. So for example, let's say I have node A here, and usually a node is encircled. Okay, this node can be a vertex or a point of intersection, or it can also represent entities like cities or places, etc., etc. Okay, now let us say you have two vertices, so A and B, and these two vertex or nodes can be connected either by an edge, and in this case, an edge looks like a straight line, okay? Or A and B can also be connected by an arc, okay? I think I will be defining arc in the next slide, but um, just for definition's sake, what we have here are nodes, for example, A and B, and an edge or a connection between the two. Okay? The connection between the two can be physically, for example, a road or a wire or a relationship between the two entities. Okay? Now, a directed graph is a graph you have where your edges are replaced by arcs. So as you can remember my example a while ago, if we have node A and you have node B, and they are connected by a line, okay? And in this case, this is an edge. We will have a directed graph if this edge is now replaced by an arc. And what does an arc look like? An arc essentially is an arrow. Okay. Uh, by definition, arcs are directed links between pairs of nodes that represent directed flow or travel. Okay. Now, just to make it complete, if you remember grade school geometry, we technically have three kinds of lines. Uh, We have this, we have this, and we also have this. Okay? If I remember correctly my grade school geometry, this is a line segment, this is a line, and this is a ray. Okay? Now, for our purpose, for the discussion on network models, no, uh, we will just simplify that these two mean the same thing. Okay, when we have an edge, so it's a line segment, we usually mean that the connection between the two is two-way. Okay, and therefore we don't need to put the two arrows. The only time we will need to put an arrow is if the direction is one way, either going to B or going to A. Okay? So now, uh, we will be discussing four types of network models. And in all of these four models, what is common in all of them is that we will be drawing a network graph. So remember what a network graph is. It is a set of nodes and edges or arcs. Okay. Now, Let me explain each one of the four models that we will be discussing by giving you a very quick example. Okay? Minimum spanning tree. What kind of problems do we usually deal with in a minimum spanning tree? Um, let's say you have a lot of computers, and you are supposed to connect all of these computers together, no, using cable wires or network cable wires. Okay, and let's say you're coming up with a computer internet shop, no? And you'd like to connect all the computers together. Okay, so for example, you have, let's say, let's do four computers, and these computers are represented by nodes. A minimum spanning tree will look like this. Well, an example of a spanning tree will look like this. So as you can see, all four nodes are connected to each other. Okay, and there is no redundant connection. What do we mean by redundant connection? In this case, if I connected this computer to this computer, then this broken line is actually redundant. Why? Because technically, computer A and computer B is able to see and talk to each other, in this case, through computer C. Okay? So I hope this very simple example gives you an idea of what a minimum spanning tree model is all about. No? What problems we are trying to solve under the minimum spanning tree model. So we'd like to look for a connection of all the nodes in such a way that the wires or the roads or the connections between the two between all the nodes is minimized. Is minimized. Okay. Next, the next type of network model that we will be discussing is called the shortest path um, problem. I hope it's very clear and easy to understand what the shortest path problem is all about and what kind of problems we will actually discuss under the shortest path. But for the sake of completeness, let me quickly discuss what kind of problems we will be solving under the shortest path. So let's say you have the H node here, and let's say you also have the S node here, and you have a lot of intermediary nodes in between. No? And let's say these are connected to each other. Okay? And what we need to do right now is to look for the shortest path from your home going to your school. Okay? So you're looking for the shortest path that will move you from your home to the school. And that, guys, is the kind of problem that we will be discussing under the shortest path model. Okay? Next, maximal flow. Let me use this example again. Okay? And let us say these nodes are connection points. And these roads are pipes, water pipes, let's say. Okay? Where water can flow through or between two intersections or two connections. Okay? And let us say you open a faucet in H, meaning you will let water flow from H, and in this case, let's say water flows from left to right, and the goal is for us to determine how much water will end up in S. And that is why the model is called maximal flow, because we are trying to look for the maximum amount of flow from an origin to a destination. Okay? And then finally, the project evaluation and review technique and the critical path method will be we will be discussing um, problems that deal with projects. Okay? And just to give you an idea, without going into detail and defining what a project is, essentially what we will be doing here is we will be answering um sige, one main question about projects in general. And what is that question? How long will the project duration be? What do I mean by this? Let me give you a very quick example. Let us say, so today, let's say today is September 11, let's say. Okay? If you start planning for your wedding today, and of course, planning a wedding involves a lot of activities like looking for a caterer, looking for a what do you call that, a couturier, uh, picking your guest lists, your ninongs and ninangs, etc., etc., taste testing the caterer, looking for a church, looking for the priest, etc., etc. Okay, so let's say you start planning your wedding today. Now, if you started planning your wedding today, per CPM, this model will be able to know the earliest date of your wedding day. Okay? Why? Because per CPM will be able to know the project duration. And the project duration is exactly how long it will take you to plan your wedding. Okay? So between September 11 and your actual wedding day, the duration in between is your project duration. And that is the kind of problem that we will be talking about in PERT CPM.